Okay, so good afternoon, everyone. Recording has started. So today we're going to cover sections 3.1 and 3.2. So far we've kind of been discussing the derivative, right? And up until now, we only had this really kind of painful way of computing it by taking the average rate of change over smaller and smaller intervals. And today we're going to learn some rules about how to find derivative functions without having to do that process, okay? And this is going to make derivatives make a lot more sense. I think once we learn these rules, we're going to be able to compute derivatives easily, we're going to be able to use derivatives, and we're going to be able to interpret derivatives. Okay, so that's where we're going. And today's class is actually, I don't have quite as much material to get through today, so I'm going to try to work in a little bit of group work back into the class, because I think it's actually really useful when the students can actually get their hands on the ideas during class. So that's what we're going to try. Office hours today, like every day that we have class, I have office hours from 3 to 4:30. SI session, is there going to be a session tonight? Mm-hmm. Okay, there will be an SI session tonight from 6 to 6:50. You have 2 homework assignments in Wiley Plus. One of them is due on Tuesday and one of them is due on Thursday. Okay, so the one that's due on Tuesday covers the material from up until last class, and then the one that's due on Thursday covers material that we'll talk about today. Okay, so 1 week to do the homework for the class that we're taking today, or the information that we're learning today. And there's also going to be a quiz. Okay, the quiz is going to be on Tuesday, and the quiz will cover the material basically from this week. Okay, so sections 2.3 up until 3.2. So that's everything from tangent lines to some derivative rules. Okay, any administrative business to take care of before we jump into the class? Anyone have any questions or comments? All right, then let's, I just want to really quickly recall some facts. So you don't need to write all of this stuff down, but I want to just remind everyone what we've been talking about so far. So I made a little bit of a recap of what we know about derivatives so far. Okay, so the first thing I want to remember is, okay, when I say f prime of a, okay, we usually use a to represent a specific input, okay? And f prime of a is going to give us a number, okay? So whatever a we put in, a could be 3 or 4 or 5, whatever we put in, then f prime of a is going to tell us something. It's going to give us another number, and that number is what we call either the derivative of f of x at x equals a, okay? Or we might say f prime of a, or it also means it's the instantaneous rate of change of f of x at x equals a. So what is the function doing for that particular x value? And it also tells us that also happens to be the slope of the tangent line to f of x at x equals a. Okay, so f prime of a is a number. When I write f prime of x, then since x is a variable, okay, I'm talking about a function in this particular circumstance. So I want to really quickly remind us what the derivative function does, okay? So it's just like, you know, one of our regular function boxes, okay? And what do? We plug in a number into the function, and we know that another number should come out the other side. And the question is, how do we find out what the right-hand side number should be based on what the input is, okay? And the thing about f prime of x, okay, is the output of the function is going to depend on the function f of x in the following way. So you give me a number, a, that's an x value. I go to that x value, which can be seen here on this graph, and I go look at what is the function doing at that point, okay? And I have 2 questions. First of all, I go up to this point and I check what is the direction that the function is going. If I was like riding a roller coaster here, which way would I be facing, right? And that tells me kind of what is the slope of the function at that point, okay? So the derivative function, it takes a number, we go to the regular function, we go to that a value, which is the input, and we check what is the slope of the original function. We check what is the slope of that tangent line. And then that is the output of the function, okay? So are we clear on what the derivative function does? It takes an x value as an input, and the output is the slope of the tangent line for that x value. Any questions about that before we move on? Okay, so some notation I want to introduce here, okay, that you may not have seen yet so far in this class is this Ddx notation, okay? So what this really means is kind of like do the derivative of. Or it could be the derivative of. Okay? So this is an operation, okay? By an operation, I mean it's kind of like a situation where I have a conveyor belt thing, only the ddx is an operation, it's not a function. The difference between a function and an operation is a function takes a number as an input, and then the output is another number. But an operation can take anything as an input. In this case, the input is the function f of x, and then the output of the operation is the derivative of that function. Okay? So this is called the derivative operator. Let me write that down, just in case anybody wants to know. You won't need to really memorize that, but that's what it's called. It's the derivative operator. Okay? And basically its job is to do the derivative of the function inside. Okay, so for example, this left-hand side says do the derivative of f of x, or it's talking about the derivative of f of x. So this left-hand side is equal to the output of when I plug f of x into the derivative operator. The derivative operator takes that function and it gives us the derivative of it. So the right-hand side of this equation would be just the derivative of f of x. Okay, and then, let's say we plug f prime of x into the derivative operator. What should that give us? Yeah, just f double prime, right? It should give us the derivative of whatever function we plug into the operator. Okay, now let's do some Leibniz notation. Let's say I have a function a function y equals f of x, and I do d dx of y. How would I represent this in Leibniz notation? Can anyone tell me? Anybody remember Leibniz notation? You're close, it's dy dx. Okay? So this was the Leibniz way of writing down, this is equivalent to, since y equals f of x, right? I could exchange y for f of x in here, and then I would just get f prime of x. Okay? So I just want to remind everyone, when I write dy dx, it's the same thing as f prime of x, as long as y is equal to f of x. Okay? It's just a different notation. Okay, and then, same deal. If g is equal to h of w, it doesn't matter if we change the letters. Okay, we can do d dw, right? That just means take the derivative with respect to w of this function. So we're just going to get dg dw, which is the same thing as h prime of w. Okay? So that's just a little notation. Anyone have a question about this operator notation here? I'm going to use it a little bit today. Yeah?
So for setting up this notation, we take whatever's in the input and place it in the denominator, and whatever that's in the output, and put that in the numerator.
Yeah, so I can imagine that looking at this, you might think, well, it's kind of like if we took a fraction d dx and multiplied it times y over 1. And you just multiply the d times the y and the dx times the 1, and you get dy dx. But that's not exactly what's going on here, okay? Because when I write this is this is a process, okay? It's not a multiplication process. It's a composition no, it's not a composition. It's really more like a plugging operation, okay? So I'm taking y as the input in this operator, okay? So it's a little bit different, okay, than doing a straight multiplication. Okay, and we'll see why maybe not tomorrow, but the next class. For example, if I have two functions, if I have y equals f of x and z equals g of x, then we will see that if I try to do the derivative of y times z, it's not going to be equal to dyz over dx, okay? It's going to actually be equal to z times dy dx plus y times dz dx, okay? So it's not exactly possible to just think of this as a fraction, okay? It's really an operation. And this is just a notation. It's not a fraction either. It's just a notation which we use to refer to this guy. Okay, so it's just a different way of writing it. But that's a little bit subtle. I'm not sure we need to get that into it at this stage. It'll become more clear as we go along, but if you get confused by any of the notation as we go, just raise your hand and I'll try to explain it more. Fair? All right, cool. So we're going to learn some derivative rules. So we're starting chapter 3 now, and, well, we're just going to dive right into it. So we have 4 rules which we're going to learn right away. So derivative of a constant function, okay, derivative of a linear function, and the derivative of a sum or a difference, and the derivative of a constant times a function. Okay, so the thing is, if we do the derivative, so how do I want to write this? So if f of x is a constant function, then f of x is equal to, say, c, where c is a real number. Okay, so think of something like f of x equals 2, or f of x equals, 1 million. Okay, so it's equal to a number. In other words, this is a linear function, right? Which is it's a linear function with just height whatever c is. So this is f of x, and this height is c, right? So it's just a horizontal line at height c. Then, okay, d dx of f of x, okay? So this means the derivative of f of x, which can also be written down as f prime of x. Oh my god, I dropped my pencil. Okay, is equal to, well, the derivative, right? Let's go back up to this thing here. It's the instantaneous rate of change of f of x at x equals a, or the slope of the tangent line to f of x at x equals a. So it's supposed to describe how this function is changing, or the slope of this function, right? Well, what's going on with the slope of this function? How is this function changing as we move from left to right? Yeah, it's not changing. So it's a slope of 0. So the derivative of any constant function is just 0, because the derivative tells us how is the function changing, and the function's not changing. So we quantify that with 0. Okay, so that's a simple rule. Let's move on to a linear function. Well, if f of x equals mx plus b, then the derivative of f of x, which, remember, the derivative of f of x is just f prime of x. That's how we write it. This is the new function. Well, if we have a linear function and the derivative is expressing how this function changes as we go from left to right, what do we think we're going to get when we do the derivative of a linear function? Yeah, just the slope, m. Okay? So you can think about it as well if you were to draw a line, right? Okay, you know that the derivative is the slope of the tangent line, right? So let's say I take a point A, and I want to draw a line which has the same slope as what the function is doing at that point. Well, guess what? The tangent line to this line is just the line, right? Okay, that's really hard to see with red there. Why don't I do it with blue? So if I do A, I want to find the tangent line. Well, it's the line which has the same slope and it goes through that point. Well, guess what? You recover the exact same line. So the slope is the same everywhere for a linear function, and we just get the slope. Okay. Next up is the derivative of a sum or a difference. So if we have two functions, f and g, and we want to find the derivative of f of x plus g of x. Okay, so first I'm adding the two functions, and then I'm plugging them into the derivative operator, okay? Then I get, this is the same as just doing the derivative of f of x and then adding the derivative of g of x. Which, of course, if I do the derivative of f of x and then I do the derivative of g of x and I add them together, another way I could write that down is f prime of x plus g of x, g prime of x. Okay, so that's a really nice rule. It says that if I take two functions and I add them together and take the derivative, it's the same as just taking their derivatives and then adding them together, right? And that seems pretty logical. But we're going to have to be a little bit careful to realize that this is actually a pretty special rule, okay? The fact that we can add two functions, take their derivative, and it's the same as just taking their derivatives and then adding them together is the only rule that's going to be like that for, okay? If we take two functions and we multiply them together, we don't just get the derivatives multiplied together. If we take two functions and we divide them, or if we take two functions and we compose them and then take their derivative, we're not going to have this nice relationship where it's like, oh, you can just do it in whatever order you want. No, this is a special thing which only counts for adding two functions together. Okay, and, well, the derivative of a constant times a function, we can get fairly easily from the previous rule, right? Because if I do the derivative of c times f of x, where c is a number, okay, so we're still working under the assumption that c is a number. So the derivative of c times f of x, well, that's multiplication is defined as repeated addition. So ddx, so c times f of x is the same as f of x plus f of x plus f of x dot dot dot, where we do this c times, right? Well, based on the previous rule, if I take functions and add them together and then take their derivative, it's the same as taking those functions' derivatives and then adding them together. So this is just the derivative of f of x plus the derivative of f of x plus dot 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 c times, which is the same as c times the derivative of f of x. C times the derivative of f of x, which is the same as c times f prime of x. So what is this all to say? This is just to say if you do the derivative of a constant times a function, you can just pull the constant out front, okay? You can just pull the constant out front, okay? It just hangs out while we do the derivative of whatever the function is. Okay, so we learned our first 4 derivative rules. So let's do a bunch of examples here, and I want you to tell me which of the following rules, if I label them 1, 2, 3, and 4, you tell me which rule is going to apply for each function when I want to do its derivative. Which rule do we think is going to apply for a? What rule should we use to take that derivative? Yeah, 1, okay? Use rule 1. And if I take its derivative, I get f prime of x is equal to, well, the derivative of a constant it tells me is 0. So 175 is a number, which is a constant, so I get 0. Easy as can be. Okay, which rule should I use for letter B? F of x equals 19x. Yeah, rule number 2, okay? It just happens to be that b is 0, but b doesn't even really matter, because all we need to do for a linear function is the derivative is just going to be the slope of that function, which in this case is 19. Okay. Let's see some more examples. Okay, which rules am I going to need to use for f of t equals 2 plus 6t? Yeah, just 2, right? I could use a combination of 2 and 4, I guess, or 2 and 3 and 4. But it doesn't need to be that complicated, because this is a linear function, okay? This has the form mt plus b, right? They wrote the b first, okay? So this is a linear function, so its derivative should just be the slope of that function, which in this case is 6. Okay, how about D? For negative 2, what should we do? Yeah, rule 1, it's a constant, f prime of x is equal to 0. Super easy. All right, let's just do f. G of x equals 25x plus pi. Huh. Which rule do I use for that one? Let me ask a question. Is 25x plus pi a linear function? Who says yes, it's a linear function? Okay. Some wavering support from some people. Can anyone offer an argument why it's a linear function? Alyssa?
Pi is a number. Pi is a number, so it's the same thing as b, so it's just 25 times 9.
Exactly. Pi is just a number. So this has the form mx plus b, where b is pi and m is 25. So what's the derivative of a linear function? It's just the slope, which is 25. All right, great. Any questions on these first 4 rules or any of the examples we just did? Okay, then I guess we'll move on to the power rule, which is everyone's favorite rule. Okay. It says that, I'm going to use a little bit of different notation this time. This time, rather than writing f of x in here, I'm just going to write what f of x is. So if f of x is x to the n, where n is a real number and n is not 0, n is a real number and not 0, yeah, okay. Then when we do the derivative of this, we get n times x to the n minus 1. Okay, let's unpack that for a second. So I have a function which looks like x to the n, okay? And when I do its derivative, what do? I take the power and I multiply it in front. Then I decrease the power by 1. So I take the original power, I multiply by that number, and I decrease the power by 1. So for example, for x to the 8, okay, I would do f prime of x is equal to 8 times x to the 7th. Okay, so I multiply down by the original power and I decrease that power by 1. Okay. How about b? Can I use the power rule to take the derivative of a function like f of x equals 1 over x cubed? I haven't had any rules yet that tell me how to do the derivative of a fraction. Is there a way I can use one of my rules to take this derivative in part B?
Yeah, you bring x up, x cubed, and then x to the negative.
Very good, Eric. Okay, so Eric says we can bring the x up. And we can write this as just x to the power negative 3. And presumably the reason was, well, now we can apply this rule, right? We just said n should be a real number that's not 0. So negative numbers are totally okay. So if I apply this rule, what do I need to do? I need to multiply down by the previous power. And then I multiply by x. And then what do I do to the power? So there's a bit of a debate here, I think, or there's a question mark. Should it be negative 2 or negative 3 times x to the negative 4? Okay, I'm hearing a lot of 4s, which is good, because if we take the rule, okay, then n, okay, is negative 3. So the power should be negative 3 minus 1. If I do negative 3 minus 1, I get negative 4. Okay, so in this case, we should use negative 3 times x to the negative 4. Okay, now I want to throw in something crazy. Okay, well, I'll say really quickly that you can use the exact same trick here for x when you have a square root. How can I rewrite? Very good, x to the 1/2. Okay, so you can do that derivative from there. Well, why don't we just do it together? Okay, so we rewrite as x to the 1/2. We want to use the power rule, so we know we should do what? Multiply by the old power, and then decrease the power by 1. So what should the new power be? Negative 1/2. Good. 1/2 minus 1 is negative 1/2. Okay, now I'm going to throw you something crazy. And the hint for part D is that we're going to need to use 2 rules at the same time. We're going to need one of our rules from the first section, and one rule, well, the power rule. So what rule do I need in addition to the power rule? Because this says, okay, this isn't just like x to the n. This is a number times x to the n. So I can't directly apply the power rule. Is there another rule I can apply first that's going to help me? Yeah, rule number 4. Rule number 4 tells me how to do the derivative of a constant times a function. So I would know how to do this derivative if this pesky 2 wasn't here. But it just so happens I have a rule which tells me how to deal with the pesky 2. Okay? So I know that the derivative of 2 times x to the 4.5 by rule 4, so rule 4 tells me that this is the same as 2 times the derivative of x to the 4.5. Okay, so all I do now is use the power rule. So if I apply the power rule, I keep the 2, and then the derivative of x to the 4.5 is 4.5 times x to the 3.5. So I get 2 times 4.5 times x to the 3.5, which is 9x to the 4.5. Okay, so what's the point of this? The point is the constant really just hangs out. Okay, if I want to find the derivative of this thing, all I have to do is leave the constant alone and make sure I carry it all the way to the end. But other than that, I just need to do the derivative of x to the 4.5. Any questions on that one? Yeah, Seth?
Is it 4.5 or like 9x?
Oh, sorry, thanks. Yeah, I just rewrote it incorrectly. It should be 3.5. Thanks for catching that. All right. Any questions on that one? Okay, cool. So we'll do one more example and then a little group work. All right, let's do G. Which rules am I going to need to use to do G? I'm going to definitely need the power rule, right? Because I got cube root of x and I got x to the minus 2. What other rules should I use? Yeah, sum or difference, because I got pluses and minuses. Anything else? Yeah, well, not 1, but 2. I think, or 2 and 4 at the same time. The 5x, right, you can think of it as a linear function. So you could apply 2. Okay, so we're going to use those rules. So basically what it says is all I have to do is the derivative of this thing and the derivative of this thing and the derivative of this thing and add them together. Okay, that's what rule 3 says. So first I'm going to rewrite this as x to the 1/3 power plus x to the minus 2 power minus 5x. And now to do the derivative, I'm just going to take the derivative of each piece individually. I get first 1/3 times x to the negative what? Negative 2/3. Right? 1/3 minus 1 is negative 2/3. And then I add. Okay, and now what I need to write is the derivative of x to the negative 2, which is negative 2 times x to the what? Negative 3. Now minus what? 5. Just 5, right? Because 5x is a linear function, so its derivative is just its slope, which is 5. Okay? All right, so that's how we would do that one. Pretty simple. All right, so now let's form our groups here, okay? So try to get into a group with like, 3 or 4 people, okay? So you can move your desks around. And we're going to work on problem 3, okay? So I wrote down, just to remind you, that this is the equation to find the tangent line. Okay, and let's try to work on finding the equation of the tangent line at x equals 1 for this function. Okay, and we're going to have to do a lot of steps here, so that's why I chose it as a group problem. So go ahead and form your groups. I'll walk around and help out if people have some questions, and give it a shot. So if you have any questions, just raise your hand and I'll come around to your group, okay?
Should we start that's what I was doing. So like when I did, I had one more step in right? So the regular function of 1 is and that got me for that. I took the derivative of that function of 1 to get x prime, and now it's multiplied by x minus 1. Yeah, so I put one into that, you get 5. And then down down to 4 1, you get 2. And then x minus
So that would be, if you take it.
Well, yeah, just, I guess if you do like negative 5x, and then like go for like that, and you negative 5, and then up 7, it would be drop to
Yeah, so the way we define
Okay, so I don't think it is here. I think it's like we're still right here.
Oh, wait.
Actually, be a variance because you want to find the equation of the tangent line, right? Its equation will be like mx plus b. Right? So what we really need to figure out is what's the m, which is b, right? That's really what we're going. So it's still stay in our equation. Yeah, right. Okay, I see it's derivatives. Where do we go from here once we got the derivatives? So remember when we from that equation to the tangent line, right? T of x equals f of a plus f prime of a times x minus a. That was the equation for the tangent line to the function at the x value x equals to a. So in terms of the problem, what do we think a is going to be for us? 1, right? So how would I get what f of a is 1? Yeah, plug in 1 to the function, right? That's how we would get f of a to be f of 1. Right? But then how would I get f prime of a? Well, we already figured out what f prime of x is. I can see it here. So if I want to get f prime of 1 yeah, put 1 in for the derivative, right?
So we're putting
We should be able to plug in any x value we want.
Okay, let's come back together as a group. Okay, let's come back together as a group. So I saw a lot of good stuff out there. okay? And I think most people noticed right off the bat that we see in the equation that we're supposed to find, okay, the equation for the tangent line, we see the derivative is showing up. So a lot of people thought, well, we just learned how to find derivatives, so why don't we just try and see what f prime of x is? So I saw this on most papers. We got f prime of x equals 3x squared plus 4x minus 5, right? Now, I just want to recall what the tangent line equation was, okay? So the tangent line equation said, if I have a function, okay, and I have an x value a, okay, so here's the function. If I want to know what is the equation of the tangent line to that function at the point x equals a, so tangent line at x equals a, we're referring to the line which is tangent to the function when x is equal to a. So we go up to the function, we find the tangent line which looks like this, and we want to know what is its equation. Well, it should have the equation of a line, right? Okay, and so what we did was we plugged in some point slope and moved some stuff around, and we saw that, well, the equation for the line is just going to be equal to this, right? So what do we need to do? I need to know, first of all, what is f of a? Well, f of a is just the height of the function when x is equal to a. So in this particular problem, what do we think a is going to be equal to? Yeah, 1, okay? In this case, our a is just 1, okay? So if I want to write down t of x equals f of 1 plus f prime of 1 times x minus 1, then what do I still need to do to kind of finish this problem out? Well, we don't need to solve for anything. What we really need to do is, this is kind of in general terms, right? I want to find the equation of the tangent line, but in particular, these two things are numbers, right? So how do I find out what those numbers are, right? f of 1 we just plug in, right? All I'm going to do is I'm going to plug in 1 to the function f of x. Well, let me do that real quick. So I know that f of 1 equals 1 cubed plus 2 times 1 squared minus 5 times 1 plus 7. So we get 1 plus 2 is 3, minus 5 is negative 2, and plus 7 I think is 5, right? How about f prime of 1? How do I get the number f prime of 1? Yeah, I'm just going to plug it into the derivative function. I did all this work here to find out what f prime of x is, so now I'm just going to do f prime of 1 by plugging it in. So it's 3 times 1 squared plus 4 times 1 minus 5. So 3 plus 4 is 7, minus 5 is 2, right? Okay, so if I want to just replace, then I get that the equation of the tangent line is 5 plus 2 times x minus 1. Okay? Yeah, Eli.
Is it minus 5 for the derivative of x because the 7 is constant, so it goes 0?
Yeah, exactly. So the 7 is, that's a great point. So maybe I should have put a plus 0 here, right? Okay, so we would add that derivative of 7, but since it's 0, we usually just don't write it. Okay? Great question. Any other questions? No? Okay, well, I just want to mention that finding the equation of a tangent line is probably going to be a very standard thing that we're going to be doing in this class. So having this formula memorized and knowing how to use it to find the equation of a tangent line of a function at a given point is going to be pretty crucial. I.e., it's almost certain to appear on the second exam. All right, so if you want more practice doing tangent lines, then come and talk with me during office hours. There's also some problems on the homework. All right, any other questions on this one before we move on? All right. Okay, so this pink box is in reference to problem 5. I just want to mention really quickly something about distance functions, okay? So earlier in the class, we learned about average rate of change, and we learned that if we take the average rate of change of a distance function, then it tells us the average velocity, right? Just telling us something, right? The rate of change of a distance is a velocity, right? If I take a distance per unit time, right? That's something like miles per hour, feet per second, meters per minute, whatever, right? This is a velocity, okay? So when I take the derivative of a distance function, okay, d prime of t is going to be equal to v of t, the velocity at time t. Okay, so we're no longer talking about average velocity, we're talking about instantaneous velocity. So earlier we said, okay, if we drive 80 miles in 1 hour, then our average speed was 80 miles an hour, right? But now we're going to think about, well, that doesn't necessarily mean I was driving 80 miles an hour the whole time, right? I could have been driving 100 for a little while and 60 for a little while, or I may have had to stop at a red light at some point, you know. So this is going to tell us our instantaneous velocity, okay? And furthermore, okay, if I take the rate of change of my velocity, right? If I take the rate of change of my velocity, then I get the rate at which my velocity is increasing or decreasing. Does anybody know the special word we have for that? Very good. Acceleration. V prime of t is a of t, which is the acceleration at time t. Okay? So this is what we want to keep in mind anytime we're talking about a function which is measuring a distance, okay, or a height or a position or anything like that, okay? So in this next problem, okay, we have a baseball which is being thrown into the air, and the height h in meters as a function of time is given by this function. So we have a function describing a distance, and we want to know what is the baseball's velocity at t equals 2. So in other words, after 2 seconds, how fast is the ball going? If this is a measurement of how high up and down it is, right? That's our goal. So what should I do if I want to find the baseball's velocity for this problem? I want to know what is v of 2 equals question mark. Any ideas or strategies of how I could start this one? Yeah, if I find the derivative of f of t, that will tell me what is v of t. So I know that v of t is equal to f prime of t, which of course I can compute using my newfound rules. Okay, so it's got three things being added together. So the derivative is just going to be the sum of each piece. For the first piece, we let the 4.9 hang out. Okay, so we get negative 4.9 times 2t to the 1. Right, but 2t to the 1 is just t, or 2t, right? Now plus, to do the derivative of 25t. 25t is a linear term, so I'm going to apply the linear rule and just take the slope of it, 25. Or you can apply the power rule, right? 25 times t to the 0. Right? 25 times 1 times t to the 0. Right? Okay, so we get 25, and then for 7, it just becomes 0, right? Okay, so I'm not going to write that last part for 7. So this is just 9.8t, negative 9.8t, plus 25, right? So I'm supposed to find the velocity when t is equal to 2. So what should I do? Plug in 2. V of 2 is equal to negative 9.8 times 2 minus plus 25, which is just 18.6. No, that's not true. It's 19.6, right? 19.6 plus 25, negative 19.6, is equal to 5.4. All right, great. So that's how we would do that problem, okay? So just remember the relationship between distance and velocity and acceleration, it's just repeated derivatives, okay? So, by the way, if d prime of t is v of t and v prime of t is a of t, then a of t is also equal to the second derivative of the distance function. Okay? So if I take 2 derivatives, then I get the acceleration. All right, any questions on that problem? All right, great. Then I'm going to move on to the next section. And the next section is we get some new derivative rules. Okay, so we're not going to do this warm-up problem, but we are going to do these new rules, okay, which is all about how to do the derivatives of exponential functions and logarithmic functions. Okay, so we know from the first chapter that these exponential functions and logarithmic functions share a special relationship, right? If we think about e to the x and ln of x, then these two functions are inverses, right? They're how we undo one another. So if I want to get an exponent out of the exponent, I use natural logs, right? And if I have something stuck in a natural log, I use exponents to get it out, right? So these two functions are inverses, and we're going to just write down some rules of how we find derivatives of these functions. And I'm going to start in the middle, actually, because I think it makes more sense to start in the middle. The rule for e to the kx, okay, is that the derivative of e to the k times x, where k here is a number, and k is not 0. Okay, so e to the 2x, e to the 3x, e to the negative 5x, okay, any of that stuff. If we do the derivative, then we get k times e to the kx. Okay, so what do? All we do is we take our original function and we multiply it by that number k. So in particular, we now get to learn why e is such a really cool and interesting number. In fact, it's the only number such that the derivative of the function e to the x is e to the x, right? Because this is e to the kx where k is 1. This is where k is 1. K equals 1. Okay? So, e to the x is this special number where if I take a look at the graph of e to the x, which looks like this, right? The funny thing about this graph is that the slope of the tangent line at any point is also equal to the height of the function. Kind of amazing, right? I just make the height of the function the exact same as the slope of the function at that point, right? If I take a look a little bit later on, right, the slope is more extreme, right, which means the slope is a bigger number. But so too is the height of the function, right? So that's kind of an interesting fact, is that e to the x is its own derivative. So if I take the derivative of e to the x, it's the easiest thing in the world. It's just e to the x again. Second derivative of e to the x is again e to the x. So that kind of answers one person's question. I think it might have been no, maybe it wasn't Brendan. Someone was asking, well, if I just take a lot of derivatives, do I eventually hit rock bottom? The answer is no. For functions like this, we don't ever just get all the way down to 0 and then 0 after that. Was that you who was asking that? Okay, that was Annabelle who was asking that. Okay. All right, great. So that's derivative of e to the kx. So a natural next step is, well, what's the derivative of a to the x where a is a number? Okay, it's a positive number. Well, the tricky thing here is I know that a is the same thing as e to the ln of a. So a to the x is the same as e to the ln of a to the x. And now I can just multiply the powers to get e to the ln of a times x. And this looks now like e to the kx. ln of a is just a number, right? It looks like e to a number times x. So I can apply the rule which I just learned, which tells me that this derivative should be ln of a times e to the ln of a times x, which by the same logic in reverse is the same as ln of a times a to the x. Okay, so the derivative of a to the x is ln of a, which is a number, times a to the x. Okay, any questions so far? This is basically how we do derivative of any exponential function. All right. So one last rule to learn for today, which is the derivative of ln of x. Okay, and it's a special one. And I'm sorry, but it doesn't really make a whole lot of sense. I mean, there are ways to make sense of it, but it turns out that the derivative of ln of x is simply 1 over x. Okay, so that's a little bit of a funny one. Now, one thing that we want to be very careful about, okay, is that a really common mistake that gets made is that people want to do the derivative of 1 over x, and they say, well, the derivative of 1 over x is ln of x. It's not quite right. It's the derivative of ln of x is 1 over x. The derivative of 1 over x would be negative 1 over x squared, right? We'd use the power rule. Okay, so just a little word of warning there to not get the order of this one mixed up. All right. Any questions before we do some examples? All right. So you're going to notice, by the way, that all through this chapter, okay, we're going to continue accruing rules, but the derivatives that we need to do are going to then just become a situation where we have like a certain number of rules that need to be applied in order to do the derivative, right? So for example, for this first problem here, f of x equals 2 times 3 to the x plus 5e to the x, we're not just going to use the rule for e to the x and the rule for a to the x. We're also going to use those rules that we learned in the previous section, right? What rules am I going to need to use from the previous section? Not in terms of numbers, but just in terms of what these rules tell us. In this particular example, we aren't going to need to use the power rule. The reason I don't need to use the power rule is I use the power rule whenever I'm doing something like x to a number, right? But the situation I have here is a little bit different. It's a number to the x. Do you see how those two are different? Yeah, so we're not going to use the power rule for this one, but we are going to use two of our other rules from the first section. Shania?
Derivative of a sum.
Derivative of a sum. Okay, and Kinsey, you got one too?
Derivative of a constant times a function.
Exactly, derivative of a constant times a function. Okay, so the first rule says, okay, The derivative of a sum tells us that the derivative of this whole thing is just going to be whatever the derivative of this thing is plus whatever the derivative of this thing is. Okay, that's all we're going to do. The second rule that we're using from the previous section is that these constants are just going to hang out. Okay, we learned how to do the derivative of e to the x, but we didn't learn how to do the derivative of 5e to the x. However, we did learn that the derivative of a number times a function, the number just hangs out and we do the derivative of the function. Okay? So the first part, I'm going to start on the left since we learned that rule, or on the right since we learned that rule first. Okay, so 5 times e to the x, the 5 just hangs out. And now we need to multiply by the derivative of e to the x, which is, as we discussed, the easiest derivative that there is to do. The derivative of e to the x is just e to the x. Very good. Okay, great. And how about the second part, or I guess the first part? I'm going to need to use that constant rule again, so the 2 is going to hang out. And then what I need to write down now is the derivative of 3 to the x. So I look back at my rules. It looks like rule number 2 is going to come into play. How should I write it down? Very good. ln of 3 times 3 to the power x. All right, so that's it. Pretty simple stuff. Okay, let's find maybe a harder one. I don't know, I guess they're all not that hard. Let's try e. Okay, I can't zoom for some reason. There we go. Okay. Man, this is messed up. Okay, so I want to do the derivative of e. Again, I think I'm going to need to use my sum and difference rule, right? Because I have a difference here. And I think I'm also going to need to use the constant multiple rule for the 15 that's going to just hang out. What other rule do I need to use? The derivative of a linear function, right? Because 17x is a linear function, right? So let's start on the left. The first part, the 15, is going to hang out because of our constant multiple rule. And then how do I do the derivative of something like e to the 1/3 times x? Well, just go back to our rule. Our rule says the derivative of e to a number times x is just that number times the function again. So in this case, what's our k value going to be? 1/3. Very good. So all I'm going to do is write k, which is 1/3, times, I'm going to rewrite the function. Sorry? Yeah, e to the 1/3 x, exactly. Okay, any questions on that first part? Okay, now I'm going to write a minus sign because I know that the derivative of a difference is just the difference of the derivatives. So now what I need to write is the derivative of 17x. Just another simple one. What am I going to get? Just the 17. Okay? You can think of that as derivative of a linear function, or you can think of it as 17x would become, by the power rule, 17 times 1 times x to the 0, which would be 17 times 1 times 1, which is 17. So that's if you want to do it using the power rule. Okay? Or you can use the linear function rule, whatever you want. All right, great. Okay. Let's do some of the ones with natural logs in them. So let's just remember, okay, of course, the derivative of any natural log function is just going to be 1 over x. So we're going to use all our rules to try to take care of part A here for problem 2. We're supposed to find the derivative of this function. And we see we have a natural log, and we have an exponential with e to the t, and we have a 4t squared. What am I going to need to use to do the derivative of 4t squared? Is that an exponential function? No. So what rule should I use? Constant I'm going to have to use, and also power rule. Very good. And then the 12, when I do that derivative, what am I going to get? Yeah, just 0. Okay, I think we got this. So first of all, The 5, of course, hangs out. So I get 5 times derivative of ln is what? 1 over x? Yeah, 1 over t, I think. We should use t because here we're doing a derivative with respect to t. Okay, so 1 over t plus derivative of 7e to the t, what are we going to get? 7e to the t, easiest derivative ever. Minus 4t squared, what does that become? 8t. Okay, we're moving a little bit faster now. Just slow me down if it's too quick, okay? And the last part, minus 0. Okay, it's that simple. Any questions on part A? No? All right, let's do another one. How about, oh, this is a good one. Let's do part C. What rules am I going to need to use to do part C? Sum? Constant times the function. Do I need to use the power rule for the first part? Can someone tell me? We actually don't need to use the power rule for the first part. Can someone tell me why? Gino?
The derivative of e to x equals e to x is just 3 for this one, so it's just the same thing.
Not quite. We're close. Alyssa, you got it?
4 e to the 3 is just a number, so we're replacing
That's right. 4e cubed. That's a number. I do e times e times e times 4, and I get some kind of number. What do I get when I do the derivative of a number? 0, right? Okay, that's a tricky one. Okay, so this one's actually going to be 0 plus. How about the second part?
3, 4, 5 times 1 over e.
Very good. Okay, so that's a tricky problem, okay? In this case, the variable's t, right? So if we had something like 4t cubed, that would be when we would use the power rule. But 4e cubed is just a number. All right, those bastards tricked us. Let's see, what do we got? 7 minutes left. Why don't we do another tangent line problem? I feel like we should do another tangent line problem. So first let's start by saying the equation of the tangent line to f of x at x equals a is given by t of x equals to what? What goes in the blank? F of a plus f prime of a times something. X minus a. Very good. Okay, that's one we need to memorize, okay? All right, so in this particular problem, they want us to find the equation of the tangent line to g of x equals 2e to the x plus 3 at x equals 0. So what's a going to be? This tells us a is 0. Okay, a is 0. So I know that t of x is going to be equal to f of 0 plus f prime of 0 times x minus 0, which is just x. Okay, so now what do I need to do in order to complete this problem? Yeah, I could do f of a just to get it over with. That's the idea here, is I need to make sure I find out what is f of 0 and what is f prime of 0. Then I'll be done, right? So let's start with f of 0. Well, f of 0 is easy enough to compute. All I do is I plug in 0 where I see an x. So 2e to the 0 plus 3, what do I get? What's e to the 0? 1. So 2 times 1 plus 3? 5. Okay. Oh, sorry, not f of 0. I guess it's g in this case. G. Sorry, used the wrong letter. Okay, so I found out what g of 0 is. What do I still need to do? Yeah, I need to find out what g prime of 0 is, which means I need to plug 0 into the derivative. But I don't have the derivative. So I find it. What's g prime of x going to be in this case? Well, we do the derivative of each piece individually. So for 2e to the x, what do I get? Easiest one ever. 2e to the x plus 0. Okay, so I'm not even going to write that. So now, what do I get when I do g prime of 0? Well, I just get 2 times e to the 0, which is just 2 times 1, which is just 2. Okay, and now I can fill in my function. T of x is equal to 5 plus 2x. Bam. It's that easy. Well, I wouldn't call it easy. I would say that it's not too difficult as long as you can remember this equation and how to apply it, right? So what do we need to do for a tangent line problem? We first need to write down what is the general equation of a tangent line. Then we need to identify what is a. Then we need to find the derivative of the function and compute the function evaluated at a and its derivative evaluated at a. Once we do those things, we got all the numbers that we need to build a tangent line. Any questions on this problem? Yeah, Christian?
I don't know, I think I just like spaced out when you like put it all together at the end for the like 5 plus 2x. Can you just explain that?
Sure. So, I started with the original equation of the tangent line, f of a plus f prime of a times x minus a. And I identified from the problem that since I'm trying to do this at x equals 0, that's my a value. Okay? So, what I need to do is t of x equals g of 0 plus g prime of 0 times x minus 0, right? So, in order to find g of 0, what I did was I took 0 and I plugged it in for x in g of x. And when I did that, I got 5. So when I saw g of 0, I replaced it by 5.
Okay.
And then for g prime of 0, what I did first was I found g prime of x. And then again, I plugged in 0 where I saw the x.
I got it.
And when I did that, I got 2. So where I see g prime of 0, I know that g prime of 0 is equal to 2. So I replaced it